In this video, we will discuss about asymptotic notations. So these asymptotic notations are used to represent the time complexity of a algorithm. They are used in algorithm analysis. An algorithm can be analyzed in two ways, with respect to time and with respect to space. So space means how much space it takes to complete that algorithm, and then time means how much time it takes to complete the execution of the algorithm. In this video, we will discuss this time algorithm analysis based on the time taken. That means time complexity of a algorithm. For the time complexity, so the time complexity, we may measure this time complexity based on the three ways. What is the upper bound of the time it takes? What is the lower bound of the time the algorithm takes to complete? And then the exact bound or tight bound or exact bound it takes to complete complete its execution. So how a simple algorithm has these three values: upper bound, lower bound, or tight bound. Basically, it depends on the characteristics of the input it takes. For the same algorithm, we can give a different kind of input. For example, if you are writing one program or algorithm for starting integer values. So in this, the size of that input, maybe it is n. So the same algorithm, suppose if you give that input, already the input is sorted. That is the one case. So already the input is sorted, and another case is the input is unsorted. That means that values are randomly scattered. So these are the two different contexts of the input, and you are going to give the same input to these two different inputs to the same algorithm. So in this case, the algorithm behaves differently. That means the time it takes to complete its execution. If it is the input, the size of the input is n. If the input is sorted, it takes some amount of time to complete it. If the input is unsorted, it takes a different amount of time to complete its execution. So that is the difference between this upper bound, lower bound, and the exact bound. Exact bound is nothing but average case, average bound. So actually, time complexity, there are three different cases: best case, worst case, and average case. We can relate that upper bound to the worst case time complexity. That means the maximum, worst case is actually the maximum time it takes to complete its execution, the maximum time taken. And lower bound can be related with the best case. That means the minimum time it takes to complete. And tight bound, we can take it as the average case. But theoretically, we cannot say upper bound is exactly as the best case or worst case, and lower bound is exactly as the worst case, and tight bound exactly as the average case. It's purely depend on the context of the algorithm as well as the context of the input. For your better understanding, just upper bound is related to the best case, lower bound is related to the upper bound related to the worst case, lower bound we can relate it as a best case, and tight bound as average case. So this upper bound of an algorithm can be represented by using big O notation. That means O of some function n, O of n. And tight bound can be represented by using the notation theta. So theta of some function n. And then lower bound of an algorithm, that is can be represented using big omega notation. This is omega of some function n. And all these notations, actually this concept is purely a mathematical concept. In mathematics we have a function, for example f of n. So this function has some definition like 2n plus 3, something like. So this upper bound, lower bound and tight bound are nothing but upper bound. What is the maximum value of this function f of n for an given input, for an input of n, and lower bound is the minimum value that this function returns for an input, for a set of input n. Input n is nothing but a range. For example, here the input n is a positive number. For the positive numbers, what is the maximum value that this function can return? And for the positive values of n, what this function can, what is the minimum value that this function can return? And tight bound is the exact value of that particular function f of n can return. So now, how it can be related to a algorithm? So algorithm can also be written as a function of the input size n. So here n is, we can take n as a input size. For a given input size, a algorithm can be represented as a function of n. So how this, by using this big O, theta and big O notations, we can able to find the upper bound, lower bound of a function. The same way we can able to find a upper bound, lower bound and tight bound of a algorithm with respect to the input size. So this upper bound, lower bound and tight bound are the time it takes to complete. So we will see one by one how that notations can be used to represent the time complexity of a algorithm. First we will start with big O notation. So a big O notations for a function f of n can be represented as big O of g of n. So if and only if there exists positive constants C and n0. So the big O notation of function f of n can be written as big O of g of n if and only if there exists positive constant c and n0. This f of n should be less than or equal to c into g of n for all the values n greater than or equal to n0. So we have to find a value n0, positive value n0, and for all the values of n that is greater than or equal to n0, this condition should be satisfied. In such way we need to find a function g of n. That means f of n should be less than or equal to c into g of n. So for example, I will explain this with one simple function. Suppose if you have a function f of n equal to 2n plus 3. So now we need to find two values c and another function g of n. So the f of n value, f of n here is 2n plus 3. So the 2n plus 3 should be less than or equal to some value. So for example, if you put 2n, so here c value is n, sorry, c value is 2 and n0 value is n. That means this is g of n. G of n is n. Whether it is true? No, we cannot say this with this 2n plus 3 is not less than 2n. So next we can find some other values. For example, instead of 2, if it is 4, then definitely 2n plus 3 is less than or equal to 4 into n for any value, any positive values of n. So n cannot be a 0. That means for all n greater than or equal to 1. So n also cannot be 0, because this f of n, here we are using this f of n as a function of an algorithm that n represent the size of the input. So we cannot use input size with 0. At least your algorithm should take some single input. So we cannot use any function, any algorithm with input 0. So we have to take that n value is greater than or equal to 1. So for all n greater than or equal to 1, this condition is true. Now this f of n can be represented as big O of g of n. So that means here g of n is nothing but n. So big O of n. We can also say like this 2n plus 3 is less than or equal to 4n square. This is also true. So we can take this c is 4 and then g of n equal to n square. So this f of n can also be represented as big O of n squared 2. This is also true. This is also true. This is also true. So the upper bound, the maximum time it can take is n, or also it can also take n square. Okay. So this is the big O notation. So big O notation, a function can be represented as a big O of g of n if and only if there exist constants c and n, n0, so where f of n is less than or equal to c into g of n for all n greater than or equal to n0. So this is the big O notation. So big O notations, it represents the upper bound of time complexity of algorithm. So next we will see the big omega notation. A function f of n can be represented as big omega of g of n if and only if there exists a positive constants c and n0. The f of n should be greater than or equal to c into g of n for all values of n which is greater than or equal to n0. So this is the definition of big omega notation. So we will see the same example. So f of n equal to 2n plus 3. So here f of n is 2n plus 3 and we need to find some values of c and n0 in which this 2n plus 3 should be greater than or equal to that c into n0 values. So we cannot say the c value as 3 and n value that n. If this 2n plus 3 is not greater than 3n, is this less than 3n, so we cannot use this, but we can say 2n plus 3 is always greater than or equal to 2n. So this is true. So now we find a C value that is 2, and then this is 2, and then g of n, that is n. For these values, this f of n is always greater than or equal to this c into g of n value. So now we can represent the same, this function f of n as big omega of g of n, that is big omega of n. So we can also write this 2n plus 3 is greater than or equal to log n, 1 into log n or 2 into log n. So 2n plus 3 is always greater than 2 into log n. So here this is c, this is g of n. So this f of n can also be represented as big O of log n. This is also true. So not big O, this is big omega of, so big omega of log n. So this is also true. So big omega of n, big omega of log of n, this is also true. But we cannot say this 2n plus 3 is greater than or equal to 2 into n square or 1 into n square. So this is wrong. So we cannot take this as big omega of n square. This is wrong. This is not the upper limit of this function f of n. So lower limit. Here this is lower limit. So this big O of n squared is not the lower limit of this function f of n. So this is actually false. So this is about the lower bound or big omega notation. So next there is theta notation. So theta notation, this is actually give the exact bound or the tight bound of the function f of n. So a function f of n can be represented as theta of g of n. So if and only if there exists two positive constants c comma n0, so where this here we need to use n1 comma n2. There are three constants, not only exactly two constants. We need to use three constants c, n1 and n2. So it's actually not c, n1, n2. So there is actually c1, c2 and n0, where so c1 dot g of n should be less than or equal to f of n, and this f of n should be less than or equal to c2 dot g of n. So that f of n value should falls between these two bounds, c1 dot g of n and c2 dot g of n. For the same function g of n, this f of n should falls between c1 dot g of n and c2 dot g of n. So we need to find such a function g of n, and this f of n can be represented by using theta notation of that function g of n. So now we use this, if I use the same function f of n equal to 2n plus 3. So 2n plus 3, we need to find a function c into c1 dot g of n, where 2n plus 3 should be less than, and then we need to find another constant value c2, but the same function n, g of n. But for that constant, this is 2n plus 3 should be greater than that c into g of n. So we can use 2n plus 3 is always less than 3n. It is true. This is true. And 2n plus 3 always greater than 2n. This is also true. So now we use the same g of n, that is n. For that c of n, if when the constant c1 is 3, this condition becomes true, and for the constant 2, this condition becomes true. So now 2n is less than or equal to 2n plus 3, and this 2n plus 3 is less than or equal to 3n. So now this function 2n plus 3 can be represented as theta of g of n. So here g of n is nothing but n. So this can be represented as theta of n. In this theta notation, we cannot use g of n as log n. For example, if we use some constant 2 into log n, and another c 10 into log n. So but 2 into log n is less than or equal to 2n plus 3. This is true. This becomes true. But this condition, so 2n plus 3 is less than or equal to 10 log n, this condition will become false. The same way, we cannot use g of n as n squared. So in this case, suppose if you use 2 into n square less than or equal to 2n plus 3, which is less than or equal to 3n squared. So in this case, this condition becomes true. 2n plus 3 is less than or equal to 3n squared. This is true, but we cannot say this condition is, but this condition is false. So exactly this function f of n, the exact bound of this function is theta of n. We cannot say theta of log n, or we cannot say theta of n square. But in upper bound, big O, we can say the function f of n can be represented as big O of n. It also can be represented as big O of n square, but it cannot be represented as big O of log n. So in the case theta notation, the same function can be represented as big O of n. The same function can be represented as big O of log n. So here we explain this. The function can be represented as big O of n, as well as this function can be represented as theta of big omega of n, and the same function can be represented as big omega of log n, but it cannot be represented as big omega of n squared. In case of theta notation, the exact bound, this function can be represented only as theta of n. It cannot be represented as theta of log n, as well as it cannot be represented as theta of n square. So it is called exact bound. So in case of time complexity, this function f of n is represented as a class of time complexity. So I already told you the time complexity depends on the input size n. What is that size of the input the algorithm takes? for the input size n, the algorithm can have a different class of time complexities. So any algorithm cannot take 0 time to complete. So 0 is not a class. So we need to start from a unit time complexity. That is unit time complexity or constant time complexity 1. So the algorithm can takes time complexity of unit time. So and then for the size of input n, the algorithm can take log n time to complete for the size of input n. And the next case is root n. It can take root n time, square root and then cube root. So that also can be included. And next is n. So and next it can take n log n time complexity. So and then n square, n cube, so on. And finally 2 power n, 3 power n, so on up to n power n. So these are the different classes of time complexities the algorithm can represent. So this is less than so the upper bound of a algorithm. For example, this in our input we find a upper bound for this function f of n square. This means all the values from n to this n power n. These are the upper bound of this particular example. So and then we also found a lower bound. So in the lower bound we find n log n. So this range of time complexities, these are the lower bound for this particular example. And this so we can say that the common class between this upper bound and lower bound is not exactly same for all the algorithms, but for your better understanding, this n, that is both common to the upper bound and lower bound. So this is the exact bound of a algorithm. So this is actually big omega notations. It belongs to, these are belongs to big O notation, and this is belong to theta notation. So this is about asymptotic notations of time complexity of algorithms. Thank you.